Good morning, APChem. This is Chapter 4 in the Zumdahl textbook. It's called Types of Chemical Reactions and Solution Stoichiometry. You'll find it on pages 116 through 161. Chapter 4 sort of segues from Chapter 3 on stoichiometry. This is chemical reactions. Mainly we are focusing on chemical reactions in water. Water is the most common solvent that we use in the chem lab. And because water is used so often, it's useful to look particularly into how water interacts with solutes and how the unique chemical tendencies of water affect the chemical reactions that occur in water. By now, of course, you know that water is a polar molecule. Its polarity is due to two things. It has unequal oxygen-hydrogen sharing in the covalent bonds, creating polar bonds. And due to its angular shape, its V shape, it's not a straight line, so it's not evenly balanced in its polarity. So as a result, water is a strongly polar molecule. Water interacts with ions by forming a sphere of hydration, as you see in the bottom right-hand corner. The ions that are positive are going to be surrounded by waters with the oxygens facing in, and the ions that are negative will be surrounded by waters with the hydrogen facing in. It's important to be able to draw those pictures. Sometimes the AP Chem test will ask you to draw the picture of what the ions look like in water. So be aware that water surrounds ions with a sphere of hydration. Ionic substances dissolved in water are no longer ionically bonded. The ions are dissociated and as a result become hydrated by water. And so ionic substances in water are not ionically bonded. Instead, they form a type of force called an ion dipole with the water molecule. The solubility of ionic and molecular substances are going to be largely variable because the interaction between the water and the ions and the attempt of ions or other molecules to attract each other, we have a competition between the attractive forces of the water and the ions and the molecules and the ions with themselves. So that competition is going to result in varying degrees of solubility. Some examples: ethanol, which is the 2-carbon alcohol, C2H5OH, is actually miscible in water. It dissolves in water at all levels, from 1% ethanol to 99% ethanol, and there's no combination of ethanol and water that do not mix. Water and alcohol are able to form strong intermolecular forces known as hydrogen bonds between the OH on the alcohol and the water molecule. Sodium chloride is quite soluble. It dissolves to around 35 or 40 grams per 100 milliliters. But it does have a limit to its solubility. Silver chloride, on the other hand, is something that is only very slightly soluble in water. So I kind of have to look at a case-by-case basis. One thing I like to look at is how well do the Coulombic forces, which are the positive-negative attractions, how well do those Coulombic forces form between water and the ions or water and the molecules, and between the ions and the ions or the molecules themselves. So Typically with ionic substances, when you start getting into the +2s and +3s and the -2s and the -3s, and also the very small charged particles, those are very attractive to themselves within the ionic compound, so they're often not very soluble. We use the general rule of thumb that like dissolves like. If you're ever asked to explain something, rule of thumbs are only there to give you the relationship. They're not there to explain it. To explain things, you want to talk about the positive and negative attractive forces, not about like dissolves like. If you use like dissolves like, the grader is going to say that's not a reason. That's a rule of thumb. But it is a useful rule of thumb. Solutions form when attractions between particles in solution are similar in strength and nature to the attractions between the pure solute and the solvent particles. We'll learn later that disorder is one of the driving forces of chemistry, and so the tendency to form disorder is always there. You just have to be able to overcome the attractive forces, which are trying to hold things together. So in the case of similar attractive forces, you're able to create strong enough attractive forces between the water and the solute to pull the solute particles apart and then allow the tendency for disorder to take over. When you have aqueous solutions, you either are going to have non-electrolytes, which would be simply molecules dissolved in water. Ethanol is an example of a non-electrolyte. Or you might have weak electrolytes or strong electrolytes. Whether an electrolyte is weak or strong depends on the degree to which the particles are separated into separate ions. One way to test for this is by testing electrical conductivity. A non-electrolyte should not conduct at all. Solutions that are only partially ionized, for example, some weak acids and weak bases, are going to conduct the electricity weakly. And that means that a light bulb on the conductivity tester will only partially light up. And solutions that are fully ionized or fully broken into ions or dissociated into ions will light the light bulb strongly. So this theory of ionization of formation of ions in solutions is credited to Arrhenius, Svante Arrhenius, and his theory of ionization was developed in the 1880s. Later got the Nobel Prize for it. So we know we have soluble ionics like NaCl that split into Na plus and Cl minus. We have soluble and strong acids such as HCl that fully ionize into H plus and Cl minus. Remember, we say the word dissociate for ionic compounds and ionize for covalent compounds. HCl is covalent, so we say it ionizes. And strong bases like sodium hydroxide dissociate completely into Na plus and OH minus. So when we say strong acid and strong base, we mean that they are strong electrolytes. Weak electrolyte examples would be something like a weak acid or a weak base. Acetic acid is a weak acid, generally designated by the arrow going in both directions between the unionized molecule and the ionized H plus and C2H3O2 minus ion. NH3 is a classic example of a weak base. It actually works with water to form NH4 plus and OH minus, but it only does that to a small percent, so it's a weak base. There are soluble polar molecules that do not ionize in water, such as ethanol. So ethanol would be an example of a non-electrolyte. When it comes to the stoichiometry of solutions, we have to have a way to take a solution and find the number of moles of solute in that solution. To do this, we use the concentration unit molarity. To do stoichiometry in solution, you have to first ask yourself, what are the particles that are reacting? Are they ions because I have a strong electrolyte, or are they molecules because I have a weak or non-electrolyte? Generally, with weak or non-electrolytes, we write the reaction as the molecules reacting because they are the most common particles. With a strong electrolyte, we write the reaction as ions reacting. So that takes practice. You have to first evaluate, stop yourself, evaluate what is the particles. What are the particles? Are they ions or are they molecules? Then you want to know what their concentrations are. What are the moles per liter? What is the molarity, capital M, of the solution? 1.0 molar means 1 mole of solute is going to be found in 1 liter of water. So, a bit of a misprint here. It says, if you're reading this along with me, that 1 mole of solution contains 1 mole of solute. It should say 1 liter of the solution contains 1 mole of solute. The Zumdahl book has about 6 examples of working with molarity problems, so you definitely want to practice those. They're found throughout pages 123 through 128. Generally, with molarity problems, when we want to find the moles, we find it by multiplying the liters times the molarity. Liters times molarity gets us the moles, and then we can do our stoichiometry problem. If we want to find the molarity, we divide the moles by the liters. If we want to find out how many liters of solution or how many milliliters of solution it takes to get so many moles, we divide moles by molarity to get liters. There are also dilution problems associated with these, where you take a pre-made solution of a certain molarity and then dilute it with water to make a new solution with a new molarity. Remember that the mathematical formula to do dilution problems is molarity 1 times volume 1 equals molarity 2 times volume 2. So if you know your initial molarity and your initial volume, you can find your new molarity and your new volume. For a dilution problem, try 4.7 pages. It spans pages 129 through 130. There are 4 different main types of chemical reactions that we talk about in water chemistry, in aqueous chemistry, and they are precipitation reactions. In precipitation reactions, you have an exchange of ions. You have acid-base reactions, in which the exchange is the proton or the H plus ion. And then you have oxidation-reduction reactions, where the exchange is electrons. Now, we talked some about precipitation in Chem 1. Generally, we're just going to review that and practice working some problems with that. For acid-base reactions, we're going to shift our focus from the way we talked about it in Chem 1. In Chem 1, we talked about acids being H+, giving H+ in water, and bases giving OH- in water, which was the Arrhenius definition. We are going to shift our focus to focus strictly on the proton, the H+ ion. We say in AP chemistry, the Bronsted definition is that the acid is the H+ donor and the base is the H+ acceptor. Or an acid is a proton donor and a base is a proton acceptor. The reaction to the upper right here shows water giving H+ to NH3 to form NH4+ and OH-. So in this particular case, water is actually a proton donor. So we say that water is an acid giving a proton to the base NH3. With that in mind, we can also look at the reverse reaction. NH4 plus acts as an acid and gives H plus to OH minus to make water and NH3. So NH4 plus is a Bronsted acid, OH minus is a Bronsted base. In oxidation reduction chemistry, we have electrons being donated from one atom or molecule to another. And so in that case, we have one particle being oxidized by losing electrons, the other particle being reduced by gaining electrons. You definitely want to study oxidation reduction reactions, since we really did very, very little with that in Chem 1. So to review, generally we talked about precipitation reactions in the same way we're going to talk about them in APChem in Chem 1. We're going to shift our focus in how we look at acid-base reactions from how we did it in Chem 1, and then we're introducing the new topic of oxidation-reduction reaction. We did not discuss that one in Chem 1. Starting with precipitation reaction. Precipitation occurs because two soluble ionic compounds are mixed together as solutions, but one ion from the first compound and one ion from the second compound actually form an insoluble mixture, and as a result precipitate out as a solid. And generally that's seen as a color and a cloudiness and maybe a clumping together, the formation of the solid. You should review your rules for solubility. The first two rules will get you about 90% of the questions, and that's realizing that nitrates are always soluble, and that the alkali metals, particularly sodium and potassium ions, and also the ammonium ion, are always soluble. When it comes to chlorides, chlorides are generally soluble with the exceptions of silver chloride, lead 2 chloride, and mercury 1 chloride. And then we have sulfate salts, which are also fairly soluble, but barium, lead, and calcium does not dissolve with sulfate. Most of your hydroxides are only going to be partially soluble, with the exception of sodium hydroxide and potassium hydroxide. Barium hydroxide is generally considered soluble, although it definitely is low in its solubility. And calcium hydroxide is the same way. It's considered soluble, but will only dissolve up to a small amount in water. Your sulfides, your carbonates, and your phosphate salts, ionic compounds, those are only slightly soluble. The exceptions being sodium, potassium, and ammonium ion with sulfide, carbonate, and phosphate will be soluble. So that's how you get them in solution. You get a sulfide, a carbonate, and a phosphate by putting it with a sodium, potassium, and ammonium. And then when you put it with some other positive ion, it's going to precipitate. So when you're looking at what is this precipitate I'm forming, you want to look at the solubility of the different products. So look at the combinations of ions from both solutions and see what's going to make an insoluble product. Once you know what that insoluble product is, then you're able to identify the precipitate. So the solutions are made by mixing solutions, which allows, because both solutions are now mixed, that allows the ions to get together and potentially combine with each other. And if you determine the combination of the positive and negative ions that's going to give you a precipitate, you can write a balanced equation for it. Anytime you have ionic products, you always want to balance the charges. So a +2 ion and a -3 ion, you're going to have 3 +2s and 2 -3s. So our first attempt at a precipitation reaction, you can try the interactive example 4.8 on page 136. Now, to describe precipitation reactions in solution, there are actually three different types of equations that can be written to do that. Each one has its good side and bad side to it. We start with the way we learned the balanced equations back in Chem 1, which is called a formula equation. A formula equation simply writes out the ionic formulas of the two reactants and the two products, including the insoluble product and the soluble product. So in the case of potassium chromate and barium nitrate, the two products are going to be in a double displacement reaction, barium chromate and potassium nitrate. So you see here I've written a balanced formula equation for that reaction. The barium chromate is the insoluble precipitate, and I know that because potassium is always soluble and nitrate's always soluble, so it must be the barium chromate. That's my insoluble solid. Now, the benefit of this is it does give the right reaction stoichiometry. It helps me do a stoichiometry problem with it, but the downside is that it's not really representing the way that the chemical formulas are actually reacting. It seems to represent them as being connected. For example, the potassium and the chromate are shown as one formula, when in fact in water those would be separated into ions. Likewise, the barium nitrate and the potassium nitrate. The only ions in this reaction that are actually connected in an ionic formula or an ionic crystal are the barium chromate. So we see that the reaction written as a formula equation is not really doing a very good job of showing what the ions are actually doing. A much improved form of this is to show all of the ions that are separated as being separated and all the ions together as being together. And so if we show the soluble potassium chromate aqueous, it's 2K pluses dissolved in water and 1 chromate dissolved in water. The barium nitrate is 1 barium ion dissolved in water and 2 nitrate ions dissolved in water. We still show the barium chromate as together as a formula because it's the ionic solids precipitate that forms. And then the K plus and the NO3 minus as should be shown as separate since they're soluble in water. So this method shows all the strong electrolytes existing as ions in solution. So the benefit is that it's more accurately showing what the state of everything is. The downside is it's very long and complicated and very busy. So one way to simplify is to show simply the ions that are forming the precipitate. So in the case of barium chromate being our precipitate, we show barium plus 2 and chromate as forming barium chromate solid. This has the benefit of cutting to the chase and showing only the precipitating ions. It does not show the ions that are not involved in the precipitation reaction. So there may be some confusion as to what's going on with those. We actually call them spectator ions. By focusing on only the ions undergoing the chemical change, we leave out the spectator ions, K plus and NO3 minus. So for practice on writing formula equations, complete ionic equations, and net ionic equations, you can try interactive example 4.9. I will tell you that APChem loves the net ionic equations for its simplicity and its focus on only the ions undergoing the chemical change. So when it comes to stoichiometry for precipitation reactions, your problem-solving strategy is to identify what are the species in the two solutions that are being combined and which of those ions in solution are going to actually react with each other and form an insoluble solid. Then you want to write the balanced net ionic equation for that precipitation reaction. You want to calculate your moles of reactants from whatever is given in the problem. You want to determine which reactant is limiting because you're mixing two solutions. One or the other may be mixed at a ratio that is the limiting reactant. And once you have the limiting reactant, you calculate your moles of product or products from that limiting reactant and then convert to grams or what other unit they ask for. So a couple examples of stoichiometry problems with precipitation reactions are 410 and 411. Okay, acid-base reactions, and this is only our first time talking about acid-base reactions in APChem. When we get to the equilibrium problems, we're going to go in much more depth on this, but I'll remind you that in Chem 1 we use the Arrhenius definition for acids, that acids produce H+, and for bases that bases produce OH-. APChem is going to focus on the Bronsted definition or the Bronsted-Lowry definition, which is that an acid is a proton donor and a base is a proton acceptor. You want to approach acid-base reactions similar to how you approach precipitation reactions by focusing on what ions and molecules are present in the reaction. And then by identifying the particles involved, you can decide what's going to donate a proton, what's going to accept a proton. So for example, if I have hydrochloric acid and sodium hydroxide dissolved in water, I can write a formula equation for that. HCl plus NaOH makes NaCl plus water, but I should remind myself that HCl is actually a strong electrolyte, and so it exists as H plus and Cl minus ions. NaOH is also a strong electrolyte, so it's Na plus and OH minus. Since I know that the combination of Na and Cl is soluble and will not precipitate, then I know that that is really the spectator ions, and that it's a reaction between H plus and OH minus to make water molecules that is my net ionic equation. H plus plus OH minus will always go to completion since water has a very low degree of ionization, so H plus plus OH minus makes water is my net ionic equation. So the reaction is going to be based on how many H pluses do you get from your acid, how many OH minus do you have from your base, and that will tell you which one is limiting and whether your solution is going to be acidic or basic after neutralization occurs. Between a weak acid and a strong base, the weak acid is not written as ionized, and so the reaction will be between the hydroxide ion on the strong base with the unionized acid molecule. So an example might be acetic acid and potassium hydroxide. The acetic acid is not ionized to any great degree, and the hydroxides and potassium ions are separated, are dissociated. The potassium ion will not react, and it will be HC2H3O2 plus OH minus, making water plus acetate will be our net ionic equation that we use for our stoichiometry problem. Hydroxide is a strong base. It's assumed to be able to react completely with any weak acid such as acetic acid. We typically call these acid-base reactions neutralization reactions. Our problem-solving strategy is to list the species present as either molecules or ions, write the balanced net ionic equation for the acid donating a proton to the base, calculate your moles of reactant, and if it's involving solution, you're going to use molarity in liters to find the moles, determine any limiting reactant, and calculate the moles of the reactant or product that you need to find. If you need to at the end, convert to grams or volume or molarity as required by the stoichiometry problem. typical application of acid-base neutralization reactions is a titration problem where you use a burette to carefully measure out the volume of acid or base that you are adding. Typically, these reactions are run until the solution is totally neutralized, and that is typically seen as a color change of an indicator. You mix a titrant, which is your known solution, with an analyte, which is your unknown solution, using a burette until you reach the stoichiometry point, and you can tell that by the indicator color change. So some acid-base reaction examples 412 through 415. Our third and final kind of reaction is the oxidation-reduction reactions. In an oxidation-reduction reaction, one atom or molecule or ion is going to be an electron donor, and the other one will be an electron acceptor. We say that oxidation is the loss of electrons, reduction is the gain of electrons. So we use the mnemonic oil rig, OIL, oxidation is losing electrons, rig, reduction is gaining electrons, to remember which is which. So oxidation reactions are reactions in where one or more electrons are transferred. If we look at the sodium and chlorine reaction, sodium reacts with chlorine by going from a neutral sodium metal atom to a sodium ion, meaning it loses an electron. The chlorine atoms are reduced because the chlorine atoms gain an electron to become chloride ions. And so the sodium is losing an electron, so sodium is being oxidized. Chlorine is gaining electrons, so chlorine is being reduced. We consider combustion reactions and many other reactions that don't necessarily involve ions as oxidation-reduction reactions. So generally it becomes useful to look at many kinds of reactions as actually oxidation-reduction, even if we consider that the electrons that are shared unevenly are actually transferred. So if you take a reaction, for the example, the reaction of hydrogen and oxygen to make water, I don't have it on the screen here, but just write down 2H2 plus O2 makes two waters. You look at that reaction, you say, oh, that's a molecule and a molecule making a molecule. But the water molecule is highly polar. So if we really look at water as being H plus ions and O minus 2 ions, you could say that the hydrogen is oxidized and the oxygen is reduced by the reaction of hydrogen plus oxygen to make water. And so when we look at oxidation states, what we're saying is if an atom has a charge, that is its oxidation state. If electrons are shared unevenly, let's go ahead and let the more electronegative atom, the one with the greater pull, assume that it has all the shared electrons. And in that case, even reactions to create polar bonds can be considered oxidation-reduction reactions. And then neutral compounds are added to zero for their oxidation states. So the first thing you have to do when doing oxidation reductions is assign oxidation states to all the elements and compounds and to every element in a particular compound in the reaction. So some basic rules for assigning oxidation state is any free atom, any free element that is not a compound, the oxidation state will be zero. Any monatomic ion, such as Na plus or Cl minus, the oxidation state will equal the charge of the ion. Fluorine is the most electronegative element, so whether it's sharing electrons or an ion, fluorine is always going to be -1. Oxygen will almost always be -2. A couple exceptions are when it's with fluorine, it's positive 2, and when it's in the peroxide ion, which is O22 minus, it is negative 1. Hydrogen's almost always going to be positive 1, the exception being with metals, hydrogen will be negative 1. Call that the hydride ion. Then we simply look at how the other elements are going to add up to equal 0 in a neutral compound. So this takes some practice, so practice the examples 416 and 417 to practice assigning oxidation states. We can use oxidation states to balance reactions. I'll show you that in class, maybe give you a little worksheet on using oxidation states to balance formula equations of oxidation-reduction reactions. This is the method for balancing oxidation and reduction half reactions. It's very common to take an oxidation-reduction reaction and split it into two half reactions, one for the oxidation step and one for the reduction step. Oxidation-reduction reactions typically occur in either acid or base solutions. If you're writing oxidation-reduction reactions in acidic solution, you're going to take the half reactions and write the separate reactions for the oxidation and the reduction steps, showing all the oxidation states of all the elements. And for each half reaction, you're going to balance all the elements except hydrogen and oxygen first. Then you're going to balance the oxygens by adding water to one side or the other. Then you're going to balance the hydrogens by adding H plus to one side or the other. Then you're going to balance the charge by adding electrons to one side or the other. Now, when you have both reactions balanced, you're going to balance and equalize the number of electrons that are being transferred by multiplying one or both of the half reactions with an integer. And once you have the number of electrons balanced and all the atoms balanced in both reactions, and you balance the two equations against each other by equalizing the number of electrons, then you're going to put the two half reactions back together, cancel out any species that are redundant on each side, and then you're going to double check yourself to see that the equations are balanced. The half reaction method for balancing in basic solutions is very similar, except that you're going to balance all the elements except hydrogen and oxygen. Then you're going to balance oxygen using water, and then you're going to balance I think I need to, you're going to balance oxygen using OH minus, and you're going to balance hydrogen using water. So looks like the way they suggest doing this is balance hydrogen using H plus, but then you want to, okay, see what they're doing now. Sorry about that. Balance oxygen using water, balance hydrogen using H plus, then you're going to add OH minus to both sides to equal the number of hydrogen ions, because you want to eliminate the hydrogen ion using water. So that would be a way to end up with only water and hydroxide, is you eliminate the hydrogen ions with OH minuses until they're all neutralized. Then you're going to simplify your reaction, you're going to get your electrons balanced, and you're going to put the two reactions back together. So some interactive examples for balancing redox reactions or oxidation-reduction reactions in acidic and basic solutions is 418 and 419. Simple oxidation-reduction reactions can work as titrations if you have a colored species that will turn color to indicate the end of the reaction. So one common one is the permanganate ion will change color from intensely purple to nearly colorless manganese 2 as it gains electrons and is reduced by a molecule like, say, hydrogen peroxide. So an example of a oxidation-reduction reaction that can be used as a titration is found on pages 158 to 159, example 4.20. So we will be doing a potassium permanganate hydrogen peroxide lab next week after we do in order to illustrate oxidation-reduction reactions and how to do a titration with an oxidation-reduction reaction.